Hello, students! Today, we're going to look at a topic that I know troubles many of you, the electronic configurations of D-block elements. But I promise you, by the end of this short explainer, this concept will be absolutely clear. So, let's begin.
You see, we all learn the standard rules for filling electrons into orbitals, right? But then, suddenly, we come across elements like chromium and copper, and it seems like they are just breaking those rules. So why does this happen? Well, this is the main puzzle we are going to solve together today.
Let's take our first case, chromium. Now, according to the Aufbau principle that we study, we would expect the configuration to be argon core, followed by 3d4 and 4s2. But what we actually observe in nature is something a little different. It's 3d5, 4s1. So the big question is, why on earth does one electron make a jump from the 4s orbital all the way to the 3d orbital?
Now listen carefully. This is not some mistake in the textbook or a random exception that you have to just memorize for your exam. Not at all. This is actually the atom itself making a choice. It is rearranging its own electrons to find a more stable, a lower energy state. And that, my dear students, is our most important clue. You see, this clue leads us to what I always call the golden rule of stability. If you can just understand this one simple rule, you will not only solve the mystery of chromium and copper, but you will also unlock a much deeper understanding of all the transition metals. So, what is this rule? Here it is. An atom gains an extra degree of stability whenever its d orbitals are either exactly half filled, that is d5, or when they are completely filled, d10. The attraction for this stability is so strong that the atom will even break the normal filling order just to achieve one of these special low-energy arrangements.
And why is this so important? Because this single rule is the key to understanding so much more. It explains why transition metals show variable oxidation states. For example, have you ever wondered why iron can be both Fe2+ and Fe3+? The answer lies in the stability of these d orbitals. This one idea unlocks a very large part of d-block chemistry for you. To make this idea very easy to remember, let's use a very simple analogy. Just imagine you were trying to find a seat in an airplane cabin. It's not just about finding any empty seat, is it? Some seating arrangements are just much more comfortable and more balanced than others.
In this little story, our electrons are like the passengers on the plane. Normally, the seats at the back of the plane, let's call that the 4s orbital, they fill up first. But there are also these special premium seats available. Those are our 3d orbitals. Now imagine if just by moving one person from the back to a premium seat, you could create a perfectly balanced and symmetrical row. Either one person in every single seat, or every seat completely full. Well, people would happily switch for that extra comfort, right? That feeling of comfort is exactly like the greater stability that the atom achieves.
Okay, the analogy is helpful, but now let's picture what is actually happening with the electrons inside the atom. We'll use the orbital box diagrams to properly visualize this electron jump that happens in chromium.
All right, look here. First, this is what we would expect based on the normal rules. 4 electrons in the 3d boxes and 2 electrons in the 4s box. But the atom sees an opportunity for something better. So, what happens next? One electron makes a jump from the 4s orbital and occupies the last empty 3d orbital. This leads us to the final, actual, stable state. Now you can see the 3d orbital is perfectly half-filled, d5, and the 4s orbital has 1 electron. This arrangement is just much more stable.
And this just shows the point so beautifully. Look at that perfect symmetry in the final state. Every d orbital has 1 electron, and all of them have parallel spins. It's this symmetrical distribution of charge and what we call maximum exchange energy that gives the half-filled d5 configuration its very special stability.
Okay, now that we've understood chromium, applying the same logic to copper will be very easy. We would expect a configuration of 3d9-4s2. But just like with chromium, the atom sees a chance to get an even greater stability. So it promotes one 4s electron into the 3d orbital.
And by doing this, copper achieves the completely filled D10 configuration, argon core 3D10 4s1. You see, a fully filled d orbital is the ultimate state of stability. It's like having a perfectly full row of all the premium seats on the airplane. So you see, chromium and copper are not exceptions at all. They are just following this higher rule of stability.
So this is not just some abstract theory we are learning. This rule about electron stability has real, visible consequences. Let's see how this concept actually shows up in the chemistry lab. A very, very common example is with the compounds of iron.
Now, if you have ever worked in a chemistry lab, you might have seen that solutions of iron salts can have different colors. This is not just a random property, It is directly connected to the very same electron configurations we have been discussing. Let's look at the two very common ions of iron. We have iron 2, or Fe2+, which has a 3d6 configuration. Its solutions are usually a pale green color. But then we have iron 3, or Fe3+, which has a 3d5 configuration, and its solutions have a very distinct yellow-brown color. Do you notice something? That Fe3+ has that special, stable, half-filled d orbital. And this is the main point to take away. The extra stability of that half-filled d5 configuration in the Fe3+ ion is what makes it behave so differently from the Fe2+ ion. This difference in their electronic structure leads to a difference in how they absorb light, and that is precisely why we see two different colors. This color change is real, visible proof of our stability rule in action.
Okay, we have covered quite a bit of ground today, from rules and exceptions to analogies and real-world examples. So let's just summarize all of this into a few simple points that you can easily remember for your exams.
First, the core idea. Stability is the most important factor. Atoms will do whatever it takes to get to a half-filled D5 or a fully filled D10 state. Second, the mental picture. Just remember that electron jumping from the 4s to the 3d orbitals, all to create a more balanced and symmetrical arrangement. And third, the real example. The different colors of iron 2 and iron 3 solutions are direct proof that this rule has real-world consequences.
So please, I want you to change the way you think about this topic. Don't look at chromium and copper as some annoying exceptions that you have to by heart. Instead, see them as clever optimizations. They are simply following a much more fundamental law of chemistry, the constant search for maximum stability.
And that is all for today. If you can just remember the core idea of stability, that mental picture of the electron jump, and the real-world example of the iron ions, I can guarantee you this topic will feel much, much lighter in your exam. All the best!